In this lesson, we're going to learn about qualitative analysis. So the very first thing that we need to do is to define what is qualitative analysis. Now in chemistry, we often perform experiments to find out about substances that we have. Alright, so when we conduct experiments to find out more about substances, we call them chemical analysis, to analyze a solution or mixture and so on. So there are in general two kinds of analysis that we can make in chemistry, either qualitative or quantitative. Now as the name suggests, quantitative means we want to find out how much of a particular substance do we have, the quantity. Alright, how much is present. So by this time we should have learned a particular experiment that we can perform to find out how much of a substance, or in particular how much of an acid or alkali we have in a solution. So an example of quantitative analysis would be titration. Now for qualitative analysis, we want to find out what is present. So for example, if we have an unknown mixture, we want to find out what substances are present in the mixture. In particular, we want to find out three possible things. We want to find the cations that are present, we want to find the anions that are present, and we can find the gases that are produced. So this chapter, essentially, we are going to look at experiments or chemical tests that we can perform to find out whether a particular cation is present in a mixture, or a particular anion or gases are present in a particular mixture. So we're going to go in this order. In this lesson, we're going to learn the test for cations, and then in the next lesson, we're going to learn anions, and the subsequent lesson, the test for gases. So if we have a solution that contains a certain cation, okay, so for example M+, in order to know what cation is present, there are two reagents that we can add. We can either add aqueous sodium hydroxide, or we can add aqueous ammonia. Okay, so adding of aqueous sodium hydroxide or adding of aqueous ammonia will allow us to establish the identity of the cation present in the mixture, in the solution. Now there is also a particular way in which we must add the reagents, and the particular way is this. We have to add the reagents drop-wise at the beginning. Alright, so drop by drop, and then followed by in excess. That means we add a lot of either sodium hydroxide or aqueous ammonia. Now what do we look out for when we add the reagents? So when we are adding drop-wise, we are supposed to look out for this, whether any precipitate, alright, or any solid is formed in the solution. If a solid is formed, we need to take note of the color of the precipitate. Okay, then after adding drop-wise, we are supposed to add a lot of the reagent, sodium hydroxide or aqueous ammonia. So what are we supposed to look out for is whether the precipitate dissolves in excess of the reagent. And if it dissolves in excess of the reagent, we need to look out for the color of the resulting solution. So let me give you an example now. So if I have a solution that contains, for example, calcium ions in there. Alright, I don't know that it contains calcium ions, so I'm going to find out by adding aqueous sodium hydroxide. When I add it drop-wise at the beginning, I see a white solid, a white PPT form. Okay, and then when I add in excess, so I add a lot in excess, I noticed that the white solid remains. It doesn't dissolve in excess sodium hydroxide. So the PPT is insoluble in excess NaOH. Okay, so this is the outcome that you will get when you add sodium hydroxide into calcium, a solution that contains calcium ions. I'll give another example. In this example, I have zinc ions. So what happens when I add aqueous sodium hydroxide dropwise? Again, I will see a white solid forming, a white PPT form. And then in step number 2, when I add sodium hydroxide in excess, I will find that the white precipitate disappears. It dissolves in excess sodium hydroxide. And the resulting solution is a colorless solution. So this is the outcome: PPT soluble in excess sodium hydroxide to give or to produce a colorless solution. So this is the outcome that I will get if I'm adding sodium hydroxide to a solution containing zinc ions. So in the syllabus, we are supposed to remember the outcomes for 8 cations, and the 8 cations are this. You have calcium, aluminium, zinc, lead, copper, iron 2, iron 3, and then we have ammonium. So these are the 8 cations where we need to know the outcomes when we add sodium hydroxide dropwise followed by in excess, when we add aqueous ammonia dropwise followed by in excess. So this table records all the outcomes for the 8 cations that I've just mentioned when we add sodium hydroxide and when we add aqueous ammonia. Now, if you can remember the outcomes by memorizing the outcomes, when we perform the test on an unknown solution and a solution that contains ions that are unknown to us, just based on the observations, we can predict what ions are present. For example, if now I have a solution that contains an unknown cation, so I'm going to add aqueous ammonia to it, and then on adding, I notice that there is a light blue solid, now light blue precipitate form. And then what I do next is I'm going to add excess of our aqueous ammonia, and what I found is that the PPT dissolved in excess ammonia to give a dark blue solution. So based on the observations that I've made in this test, I can conclude that the unknown contains copper 2 ions. Okay, so you can see that the observation matches whatever that's given in the table. Now, there is a test that is quite special, which is for ammonium ions. If you take a look at ammonium ions, over here when you add sodium hydroxide, there's actually no precipitate that's formed, but in the test they will require you to do some warming, and when you warm the mixture, ammonia gas will be produced. Alright, how would we detect ammonia gas? Ammonia gas is pungent, okay, and it will turn moist red litmus paper blue. Alright, we're going to revisit that when we look at the test for gases. Now, still on the test for ammonium ions, you notice that we don't add aqueous ammonia to test for ammonium ions, because it doesn't make sense, because aqueous ammonia will produce ammonium ions in solution. So there is it makes no sense to add something that will produce the ions to test for the ion. Next, if we compare the tests for lead and aluminium, okay, if we look at tests for aluminium cation and lead, you will notice that the observations are the same for sodium hydroxide and for aqueous ammonia. So by using these two reagents, there's no way for us to distinguish between aluminium and lead ions. Meaning, if we have an unknown solution and on adding sodium hydroxide we get a white PPT soluble in excess, and then when we add aqueous ammonia we get a white PPT insoluble in excess, we cannot conclusively determine that it contains aluminium or lead. So we need to perform an extra test. We can actually add sodium chloride to the solution, and what happens is that lead ions will give a white precipitate, and the white precipitate is actually your lead 2 chloride, whereas aluminium will not give any precipitate. Okay, we can also use potassium iodide, which will give a yellow precipitate with lead but no precipitate with aluminium. Now, one very important point to remember for the is this: when you add sodium hydroxide or aqueous ammonia to a cation and a precipitate, a solid is formed, the identity of the solid is a metal hydroxide. Okay, so for example, when I have a solution of iron 2 ions and I add sodium hydroxide, I will see a dirty green precipitate. Now, what is the dirty green precipitate? The dirty green precipitate is actually your iron 2 hydroxide. Okay, if I have a solution of iron 2 ions and I add aqueous ammonia to the solution, I will see a dirty green precipitate. What is the identity of the dirty green precipitate? Is also iron 2 hydroxide. Now, you may be wondering, by adding aqueous ammonia, where did the hydroxide come from? You have to recall in the topic of acids and bases that ammonia is a weak alkali. So when ammonia is dissolved in water, aqueous ammonia, it actually ionizes to produce ammonium ions and hydroxide ions. So it's the hydroxide ions that is reacting with your iron 2 to form the precipitate. So in summary, all the precipitates that are formed in the test for cations are metal hydroxides. Now, why am I stressing on that is this: because when a common mistake that students make is that we will often ask you for the identity of the precipitate. For example, when adding aqueous ammonia to iron 2 ions, and students will always come up with wrong answers like iron ammonium or iron 2 ammonicate. Alright, so very importantly, remember that the precipitates that are formed in the test for cations are metal hydroxides. If I'm testing for copper 2 ions, the precipitates that are formed, regardless of whether I'm adding sodium hydroxide or aqueous ammonia, they are copper 2 hydroxide. When I'm testing for lead ions, when I add sodium hydroxide, the white precipitate form is your lead 2 hydroxide. It's always the metal hydroxide. Another commonly asked question in this part in the test for cations is in the writing of ionic equations. Okay, if you have forgotten what are ionic equations or how do we write them, please revisit the video on writing chemical equations. So very often you'll be asked to write an ionic equation to represent the formation of a particular precipitate. So for example, in this case, iron 2 hydroxide. So how do we write the ionic equation to represent the formation of the dirty green precipitate iron 2 hydroxide? Now in writing ionic equations for precipitation reactions, there is a shortcut, and the shortcut is this, that you write down the formula of the precipitate first. So iron 2 hydroxide. The fact that it is a precipitate means that it is in solid state. Next thing is that we need to write down the ions that make up this precipitate. So the ions that make up iron 2 hydroxide will be Fe2 plus and 2OH minus. In precipitation reactions, the ions must be mixed in aqueous state. So you need to write in aqueous. So that is the ionic equation for the precipitation of iron 2 hydroxide. So what we have seen here again is the shortcut for writing ionic equations for precipitation reactions. First, we write down the formula of the precipitate, and then in the reactants, we simply need to write out the ions that make up the precipitate, and they are always 100% of the time in aqueous state. So once you have written down the ions, that is the complete ionic equation. If you don't believe me, you can write the chemical equation for any precipitation reaction, and then you go through the standard procedure of cancelling out your spectator ions. You will arrive at the equation that is obtained using the shortcut. So let's try some questions now. In this question, they are adding aqueous ammonia to different cations, and they're asking which one will give a PPT that dissolves in excess ammonia. So let's recall aluminium. Aluminium, when adding aqueous ammonia, will give a white PPT, but it will be insoluble in excess aqueous ammonia. Iron 2 will give a dirty green precipitate. Again, it is insoluble in excess ammonia. Iron 3 will give a reddish brown precipitate. Again, insoluble in excess. Zinc will give a white PPT that is soluble in excess aqueous ammonia. So the correct option is D. Now the only ion that will give a PPT that will dissolve in excess of sodium hydroxide and aqueous ammonia is zinc. I repeat again, the only cation that will form a precipitate but dissolve in excess of sodium hydroxide and aqueous ammonia is zinc ions. So in this question, an unknown solution X is added to aqueous ammonium chloride, and then on heating a gas is produced which turns the color of moist litmus paper. Now I hope by looking at the diagram and looking at the procedure, you can guess that it's actually a test for cation, and the cation is given in this question is ammonium. So we have to recall, how do we test for ammonium ions? Is by adding sodium hydroxide. So solution X is sodium hydroxide, and what happens when we add sodium hydroxide and we warm the mixture is that ammonia gas will be produced, which will turn your moist red litmus paper blue. So the correct answer is A. Now in this question, the scenario described is that the student forgot to add the sodium hydroxide dropwise. So it was added like in excess from the start, and because of that, the precipitate that was supposed to form was not observed. So essentially the scenario is describing this, that which ion will dissolve in excess of the reagent. So if we look at the four options, Again, the option that's correct is option D, because zinc will form a white precipitate that dissolves in excess sodium hydroxide. For A and B, they will both form a white precipitate. Even if you add too fast, the precipitate is not going to dissolve, so we're still going to see it. So A and B are the wrong option. C is wrong also because ammonium ions do not give any precipitate. In this question, we are supposed to determine which observations are correct when adding sodium hydroxide and aqueous ammonia to zinc ions. If you can recall a few questions back, I mentioned that zinc ions are the only ions that will give a precipitate but dissolve in excess for both sodium hydroxide and aqueous ammonia. So if you can recall that, that will allow you to very easily determine the answer to be A. So we have looked at the test for cations in this lesson. Essentially, we add either sodium hydroxide or aqueous ammonia. We add it drop by drop, observe for any precipitate form and the color of precipitate. Followed by step number 2, we add in excess. So we add until the test tube is like 3/4 full, and we observe if the precipitate dissolves. If it doesn't, it's insoluble. If it dissolves, we need to take note of the color of the solution form. And based on the expected observations, we can therefore determine the ion that's present in the unknown solution.